For the following piecewise function, algebraically determine whether f of x is continuous at x equals 0 and x equals 3. So we're going to determine if this function is continuous at x equals to 0 as well as x equals to 3. So to determine if a function is continuous at a specific point, there are three criteria that need to be fulfilled. We're just going to summarize them up here. So the first criteria is going to be that the function is defined. It needs to be defined at x. I'm going to refer to that as the dot. And what that means is that if it's graphed, will there be a point at the y-coordinate corresponding to x? Okay, so it needs to be defined at x. The second criteria is that the left-hand limit has to equal to the right-hand limit. So the left-hand limit has to equal to the right-hand limit. Okay, so another way of expressing this would be that the limit as x is approaching a from the left of function f of x has to be the same as the limit as x is approaching a from the right of f of x. And then the third criteria is going to be that the limit has to be equal to the dot. Okay, so the limit that we find in step 2, if this criteria is fulfilled, we have a limit. That limit has to equal to the value corresponding to x, so the f of x. So let's have a look at these two examples here. So x equals to 0. So let's first assess it using the criteria number 1. Is there a dot? Is it defined at x equals to 0? Well, if we take a look at the definition of this piecewise function, we see that it is indeed defined. So when x equals to 0, y equals to 1. So we can say that f of 0 equals 1. So it passes that first criteria. The second criteria is the left-hand, the right-hand limit the same. So the left-hand limit here equals the limit as x approaches 0 from the left of f of x. Now that function, when x approaches 0 from the left, that means that we're going to be, x is going to be slightly smaller than 0. So we're going to use this definition for f of x in this piecewise function. So we can rewrite this as the limit as x approaches 0 from the left of x squared minus 2. And now we can substitute in 0. So it's going to be 0 squared minus 2 equals negative 2. So that's the left-hand limit. And then the right-hand limit, so this time it's going to be the limit as x approaches 0 from the right of f of x equals, well, so as x approaches 0 from the right, so x is going to be slightly larger than 0. So we're going to be using the function definition of 1. So this is going to say that the limit as x approaches 0 from the right of 1. So here, this is a numerical constant. The function is a numerical constant, which means that the limit will be that numerical constant. The limit is 1. So here we can now see that the left-hand limit is not equal to the right-hand limit, which means that the limit does not exist. And what it means here in the context of this function is that this function is discontinuous at x equals to 0. So actually what we can even write here is that the limit as x approaches 0 of f of x is an empty set. So that is for x equals to 0. Let's do the same thing for x equals to 3. Just going to try and, I couldn't do that. I couldn't move that. Okay, so x equals 3. Let's just leave it here then. X equals to 3. So we're going to go through the same steps. So obviously when x equals to 0, we never get to step 3 because there is no limit. So we will never evaluate whether the limit is equal to the dot. Okay, so we can actually maybe say step or criteria number 3 is not applicable here because we failed criteria number 2. So do we have a dot? Is the function defined at f of 3? So when x equals 3, it is indeed defined. The function is going to equal f minus x. So it's defined as 4 minus 3 equals to 1. So it has a point at x equals 3. Second criteria, evaluating the two limits from the left and from the right. So the left-hand limit here is going to be the limit as x tends to 3 from the left of f of x. So we're looking at x values that are slightly smaller than 3. So the function is going to be defined as 1. So we're going to get the limit of, or as x goes to 3 from the left of 1 will equal to 1. So that's your left-hand limit. Your right-hand limit. So the limit as x tends to 3 from above this time of f of x. So this time x is slightly larger than 3, so we're looking at the function being defined as 4 minus x. So we can write it as limit as x goes to 3 from above of 4 minus x. We substitute in the x. We're going to get 4 minus 3 equals to 1. So now we can see that the left-hand limit equals to the right-hand limit, which means that the limit exists. Okay, and specifically the limit as x goes to 3 of f of x equals to 1. That was criteria number 2. Criteria number 3, now we need to make sure that the limit we got of 1 equals the value of the dot. And it is indeed the same. So here we can now say that the limit equals the dot. Okay, and we can also write this as the limit as x tends to 3 of f of x equals to 1, which is equal to f of 3. That was the dot, right? And so what this means mathematically is that the function is continuous. At x equals to 3. I just realized you can actually see the stuff I wrote on the edge here. So here I just wrote 1. That should belong up here. And over here, let me just clean this up a little bit. So this should say f of x. This one here should be equal to 1. And over here, x equals 2. continues at x equals to 3. Okay, so that's all of this is question A. Now in question B, they're asking us to sketch this function, so I'm going to just do that on a separate sheet here. So in B, we're going to sketch. So we have our x-axis here, and we have our y-axis here, which is f of x. And then this piecewise function had 3 parts. It had the part when x is less than 0. So to the left of the y-axis, this is going to be the region where the function is defined as x squared minus 2. And that was when x is less than 0. So that's to the left of the y-axis. And then we have the region from the y-axis 0 up to, but not including 3. So I'm going to indicate that region, or the boundary of that region, with a dotted line. So we know that this point right here, the x-coordinate here is 3. And here the function is defined as 1, and it's defined between 0 greater or equal to 0 and less than 3. And then finally we have the function that's defined above, or the part of the function is above x equals to 3, so x greater or equal to 3, and the function is defined as 4 minus x when x is greater or equal to 3. So now we're going to sketch it. So on the left-hand side we have x squared minus 2. This is a parabola that opens up, and the negative 2 means that it's been shifted 2 steps down. It's been transformed. So it's been shifted 2 steps down, which means that the y-intercept here, which is not included, is going to be at negative 2. So it's going to look something along this line. Okay. Then between x equals to 0 and x equals to 3, the function equals to 1. So the y-intercept here is going to be 1. We include that point, but we exclude 3. And then finally, when the function is 3 or greater, it's a linear function with a negative slope. So it's going to be looking something like this.